Sir, you can start now, sir.
Okay, ma'am. Thank you so much. Good evening, students. Today we are going to discuss the solutions for the remaining numerical problems for which I gave you test on moving charges and magnetism and the magnetic properties of matter. Okay, that is magnetism and matter. So last week I gave you a question paper containing 30 multiple choice questions on this particular subject. Yesterday itself we have one second. Yes, sorry for the interruption. So actually I gave you a question paper containing 30 multiple choice questions last week, and yesterday we had discussed the solutions for the first 15 numerical problems. Today we are going to discuss the solutions for the remaining problems. Okay, from problem number 16 we are going to discuss now. So I will be sharing my screen with you. So here I have shared my screen with you. So this is question number 16. A uniform conducting wire of length 12A and resistance capital R is wound up as a current carrying coil in the shape of an equilateral triangle of side A and a square of side A. Okay, the magnetic dipole moments of the coil in each case respectively are. So they are telling us that there is a uniform conducting wire having some length and resistance R is wound up as a current carrying coil in the shape of an equilateral triangle of side A, square of side A. Okay, they are asking us to find out the magnetic dipole moments of the coil in each case. Okay, so for that what we have to do is, here you see the length of the conducting wire as given in the problem is L equal to 12A, and the resistance of the uniform conducting wire is capital R, and we all know very well that the magnetic dipole moment is given by M equal to NIA. Okay, where N is the number of loops and I is the current in the loop and A is the area of the coil. Using this formula we are going to calculate the magnetic dipole moments. We all know very well here for an equilateral triangle, okay, the total wire length given in the problem 12A should be equal to N into perimeter of the triangle. Okay, N means the number of loops on that equilateral triangle. The total wire length is 12A as given in the problem, and we should multiply the number of loops N with the perimeter of the triangle to get the number of loops. Okay, N. So here 12A equal to N into 3A, because we know very well the perimeter of the triangle is 3A, because all the three sides having the equal length A. Okay, so 12A equal to N into 3A, that will give you N equal to 4. Okay, that you can easily judge from the diagram. So this is the triangle, and here we have found out that the total number of turns or total number of loops here is N equal to 4. So in the formula for magnetic dipole moment, we have to find out the area. Okay, because here you have area. So the formula for magnetic dipole moment is M equal to NIA. So for that we need to calculate the area of this equilateral triangle. So the formula is root 3 by 4A square. And now the magnetic dipole moment, magnetic moment formula, M equal to NIA. So for this equilateral triangle, N equal to 4 into I into area is root 3 by 4 a square. That will give you I into root 3 a squared or root 3 ia square. This is the first case. For case 2, we have the square of side A, and the total wire length is 12A, and that should be equal to n into perimeter of the square. Okay, so perimeter of the square means it is 4A. So the total wire length 12A equal to n into 4A. So from this you can find out the value of n, or the total number of loops, that is 3. And now we have to calculate the area of the square, that is given by capital A equal to small a square, and magnetic dipole moment capital M equal to NIA. So capital M equal to this thing 3ia squared. Okay, 3ia squared, because n equal to 3 and I into a squared. So we have found out the magnetic moments, and now we have to see which of the 4 options contain these values, that is option A. Okay, so now option A is the right answer. Okay, so then question number 17, a wire of length L. Okay, a wire of length L meter carrying a current of I ampere is bent in the form of a circle. Its magnetic moment is. Okay, so once again you have a wire of length, and that wire is bent in the form of a circle. We need to find out the magnetic moment. So same formula, M equal to NIA we are going to use. Only thing is we need to find out the radius of the circle. Okay, so 2 pi r equal to L. How did we get this equation? Because the wire of length L is bent in the form of circle. Okay, that means the length of the wire should be equal to the circumference of the circular coil. So 2 pi r equal to L. That means r equal to L by 2 pi. Okay, r equal to L by 2 pi. And now the area of the circle equal to pi r square. So pi into, instead of r you need to put L by 2 pi the whole square. That will give you L squared by 4 pi square, and this pi and this pi squared will be cancelled, and you will be left with L squared by 4 pi. Okay, this is the area of the circle. So now the magnetic moment is I into A. So A is L squared by 4 pi. So that is option D. Okay, I L squared by 4 pi. Then question number 18. Okay, question number 18. If you want to solve this, you need to just carefully observe the cases. Following figures show the arrangement of bar magnets in different configurations. Each magnet has magnetic dipole moment M. Which configuration has the highest net magnetic dipole moment? Here you see you have 4 configurations. Okay, so this thing and this thing, second configuration, where the 2 bar magnets are arranged like this. This is the first configuration. The second thing is like this, and the third configuration is like this, inclined at an angle 30 degree. And in the fourth configuration, the magnets are arranged like this, inclined at an angle 60 degree. What they have asked is which configuration has the highest net magnetic dipole moment. Okay, for that we need to apply the formula. Okay, M net, that is the net magnetic moment, is given by root of M squared plus M squared plus 2M squared cos theta. Okay, how did we get this? So that is M1 plus M2 whole square. Okay, M1 plus M2 whole square. So let me write that equation here for your better understanding. How did we get this equation? So here M net. Okay, the net magnetic moment is given by vector M1 plus vector M2, the whole square. and what you have to do is you have to take the square root of this. So when you take the square root of this, what you will get? So m1 squared plus m2 squared plus 2 into m1 dot m2. Okay, this is the equation, and this will be m1 squared plus m2 squared plus this is 2 m1 dot m2 cos product. So m1 m2 cos theta between this m1 and m2. This is the general thing. Okay, this is the general expression, and this m1 and m2, instead of this we are just taking it as m and m. Why I am taking it m and m? Because in the question they haven't mentioned that the bar magnets are of different magnetic moments, which means we can consider that both have the same magnetic moment, capital M. Okay, because they are telling that each magnet has the magnetic dipole moment, capital M. So the two bar magnets have the same magnetic moment, capital M. So in this formula, okay, m net equal to root of m1 plus m2 the whole square, we can consider, we can take it as m. Okay, m1 equal to m2 equal to m. So that's why we are getting this equation. Okay, m squared plus 2m squared cos theta. And after applying this, you need to know the value of this theta, cos theta, because the maximum value of the net magnetic moment will be obtained when your cos theta value is maximum. For the cos theta value to be maximum, what is your value of theta? Theta should be minimum, right? Theta should be minimum. Okay, so you need to observe which configuration has the lowest value of theta. Here you see, for this configuration the theta value is 90 degree. Okay, initially you see here for this configuration the theta value is 90 degree, and for this configuration north and south pole is arranged exactly anti-parallel to the south and north pole. This means here theta will be 180 degree. Okay, here theta will be 180 degree, and for the next configuration it is 30 degree, and for the fourth configuration it is 60 degree. So among the four configurations, theta equal to 30 degree is the minimum value. So for the minimum value of theta, cos theta will be maximum. So for theta equal to 30 degree, m net will be maximum. So option C is the right answer, because it is having theta equal to 30 degree. That's the minimum value among all the four configurations. Then question number 19, you see a bar magnet of length L and magnetic dipole moment capital M is bent in the form of an arc as shown in figure. The new magnetic dipole moment will be, okay. So here they are mentioning that there's a bar magnet of length L and magnetic moment M bent in the form of this arc, as you can see from the diagram. And that arc is making an angle 60 degree at the center. Okay. So the radius of that circle formed by that arc is taken as small r. Okay. Now what is the new magnetic moment for that bar magnet? Okay, because initially it is in the form of rectangle. The bar magnet is in the form of rectangle. Now it is bent in the form of arc. For that the magnetic moment will be changing. What is the new value of magnetic moment? That we need to find out. So here you see the magnetic moment formula is capital M into small m, capital M equal to small m into small l, where small m is nothing but the pole strength. Okay, small m is nothing but the pole strength, and L is the length of the bar magnet. So according to the question, they are telling that the bar magnet of length L is bent in the form of arc. Okay, so this arc is considered to be the arc length. Okay, so here you see this arc is considered to be the arc length. So this arc length is considered to be the linear displacement. So linear displacement equal to radius into angular displacement. This is the formula. Linear displacement equal to radius into angular displacement. So based on this, we all know very well, this is the linear displacement from here to here. Okay. From here to here, you have the linear displacement. That is the length of the bar magnet. That is small m equal to radius is mentioned in the diagram as r into angular displacement. Angular displacement is 60 degree. That is nothing but pi by 3. Okay, pi by 3. L equal to r into pi by 3. And that thing we can see from the solution here. Okay. 1 second. Here you see L equal to pi by 3 into r or r into pi by 3. That will give you r equal to 3L by pi. Now the new magnetic moment is given by small m into that L. Okay, small m into L. So that will be r. So r equal to 3L by pi. Small m into 3L by pi. That will give you 3ml by pi. So here ml means capital M. Okay. So 3 capital M by pi. That is in option B. Okay. 3 capital M by pi. That is in option B. And question number 20 is here. A bar magnet having a magnetic moment of 2 into 10 power 4 joules per Tesla is free to rotate in a horizontal plane. A horizontal magnetic field B equal to 6 into 10 power minus 4 Tesla exists in the space. The work done in taking the magnet slowly from a direction parallel to the field to a direction 60 degree from the field is. Here they are keeping a bar magnet in an external magnetic field and they are asking us to find out the work done in rotating the magnet. Okay, work done in rotating the magnet from a particular angle to another angle. For that we have the equation or the formula. So this is the general formula you see. So work done. Okay. So work done is equal to MB. Okay, as you can see from this equation. So this thing. Work done is equal to MB into cos theta 1 minus cos theta 2. Okay. So that means theta 1 is the initial angle, theta 2 is the final angle. So M value we have, B value we have. Okay, as it is given in the question. Cos theta 1 minus cos theta 2. Theta 1, since it is considered to be parallel to the field, theta equal to 0 degree. And the second case, theta 2 equal to 60 degree. So it's a direct substitution. Nothing much here. So W equal to MB into cos 0 degree minus cos 60 degree. Cos 0 value is 1 and cos 60 value 1 by 2. And M and B you can substitute and you can find out the value, that is 12 by 2. That is 6 joules. Okay. So this is the expression for work done. And question number 21. The relation among the 3 elements, Earth's magnetic field, namely horizontal component H, vertical component V, and dip delta. Okay, this is symbol delta, where V equal to total magnetic field. So what is the relation among the three magnetic field? Okay, 3 elements actually. The Earth's magnetic field, that is a horizontal component H, vertical component V, and dip delta. So what is the relation among the 3 parameters? You need to choose the correct option from the four options. For that you need to draw this diagram. Here you see this is the horizontal component and this is the vertical component. The angle made with the horizontal is called a dip. Okay, angle made by Earth's total magnetic field with the horizontal component is called the dip delta. So from this diagram, what is the value of this V? V is nothing but V sine delta. Okay, from the diagram itself, you can find out the solution. It's a very simple solution here. From the diagram, you can see this is the opposite side, right? Opposite side is nothing but V, that is the vertical component, and V equal to B sine delta, and this H is equal to B cos delta. Okay. So all these things you can easily find out from the diagram itself. So option B is the right answer. Okay, H equal to B cos delta, V equal to B sin delta, option B. Then we have theta 1 and theta 2 be the apparent angles of dip. The next question, question number 22. If theta 1 and theta 2 be the apparent angles of dip observed in two vertical planes at right angles to each other, then the true angle of dip theta is given by. Okay, here you have two angles of dip observed in two vertical planes at right angles to each other. Okay, then the true angle of dip theta is given by. They have given you four options. You need to choose the right one. And let us move on to the solution here. So this is plane 1 and this is plane 2. Okay, plane 1 and plane 2. So they have given that plane 1 and plane 2 are oriented at right angles to each other. Plane 1 and plane 2. Okay, that is, I think it's okay, please wait. Okay, the two vertical planes at right angles to each other. For that, theta 1 and theta 2 be their apparent values of dip. Okay, so here you can see this is theta. With the magnetic meridian, it is making an angle theta. Okay, because it is 90 degree. The angle between this plane 1 and plane 2 is 90 degree, and the angle made with the magnetic meridian is theta. So the whole angle is 90 degree. That means the remaining angle here is 90 minus theta. That means, so this is BH cos theta and this is BH sin theta. Okay, BH cos theta and BH sin theta. So tan theta equal to V by H. Okay, tan theta equal to V by H. V means this vertical component and H means the horizontal component. So tan theta equal to V by H. That means cot theta is equal to H by V. Okay. Now tan theta 1. Tan theta 1 means it is V divided by H cos alpha. Okay. H cos alpha. So that alpha is nothing but the angle considered by us. Okay. Alpha is nothing but the angle considered by us. So tan theta 1 equal to V by H cos alpha, and cot theta 1 equal to, that means here you need to take the reciprocal. So cot theta 1 equal to H cos alpha by V. This is cot theta 1 and this is tan theta 2. That means V by H sin alpha. So when you take the reciprocal, that will be cot theta 2. So here also you need to take the reciprocal H sin alpha by V. Okay. So here you have cot theta 1 and here you have cot theta 2. So you have to square both these terms and then you have to add it. Cot square theta 1 plus cot square theta 2. That will be H squared cos squared alpha by V square plus H squared sin squared alpha by V square. Then what you have to do? You have to take H squared by V squared as common. Within the bracket you need to take cos squared alpha plus sin squared alpha. So this is actually 1. Okay. So cot square theta 1 plus cot square theta 2 equal to H squared by V squared ultimately, and H squared by V squared is nothing but cot square theta from this equation. So this is cot square theta and it is option B. Okay. And the second and the 23rd question, you have two bar magnets having same geometry with magnetic moments capital M and 2 capital M. Okay. 1 second, I will be back. Okay. Okay, now we shall continue. So here you see we have two bar magnets having the same geometry with magnetic moments M and 2M. Okay, capital M and 2 capital M are firstly placed in such a way that their similar poles are on the same side. And then its period of oscillation is T1. Now the polarity of one of the magnets is reversed. The time period of oscillations becomes T2. Okay. So we have two bar magnets and then they are made to oscillate. Okay, they are made to oscillate. Then initially they are keeping the magnets in such a way that their similar poles are on the same side. There its period of oscillation is T1, and when you reverse the polarity of the magnets, the time period of oscillations becomes T2. Now they are asking us what is the relation between this T1 and T2. So for that, we should first write the formula for the time period of the bar magnet, time period of oscillation of the bar magnet. That is T equal to 2 pi root of capital I by mh, where m is the magnetic moment of magnet, I is the moment of inertia of the magnet, and h is the horizontal component of Earth's magnetic field. And when you have same poles of magnets are placed on the same side, then the net magnetic moment is given by m plus 2m. Okay, m plus 2m, because simply when you take the similar poles on the same side, then your magnetic moments are simply added up. So this is m and 2m. So when you keep it in such a way that the similar poles are on the same side, that means the total magnetic moment is this m plus 2m. Okay, so m plus 2m, that is 3m. Now the time period of oscillation is T1 equal to 2 pi root of I by m1h. Instead of m1 you need to put 3m, so that will be 3m. So T1 equal to 2 pi root of I divided by root T equal to T1 equal to 2 pi root of I by 3mh. And second case, when opposite poles of the magnet are placed on same side, then the magnetization or the magnetic moment of one magnet opposes the other. Okay, so you need to find the difference of the magnetic moments, that is 2m minus m. Okay, that will give you m. So now the time period is T2 equal to 2 pi root of I by mh, m2h, that is mh. So here T2 equal to 2 pi root of I by mh. In T1 it is root 3 in the denominator, and in T2 it is root m in the denominator. Okay. So here root 3 is the larger value, but it is in denominator. That will make T1 lesser than T2. Okay. From the values of T1 and T2, you can find that this T1 is lesser than T2. Because in T1 you have root 3 in the denominator, inversely proportional relation. The larger value in denominator makes this T1 lesser than T2. Okay. Right. Then question number 24. A bar magnet is oscillating in the Earth's magnetic field with a period capital T. What happens to its period of motion when if its mass is quadrupled? Okay, they are telling that there is a bar magnet and it is oscillating in the Earth's magnetic field with a period T. What happens to its period of motion if its mass is quadrupled? Mass is quadrupled means the mass is made 4 times the initial value. Okay, suppose initially if its mass is 3 kilogram, so now if the mass is quadrupled, okay, what happens to the final mass? It is 4 times the initial value, that is 4 into 3, that will be 12 kg. So mass is quadrupled means the mass is made 4 times the initial value. So if the mass of the bar magnet is made 4 times the initial value, what happens to its period of motion? Period means the time period of motion. They are asking. They have given options. Motion remains simple harmonic with new period equal to T by 2. motion remains simple harmonic with new period equal to 2t. Okay, like that, they are having the four options. So we shall see. The time period is given by, in general, t equal to 2 pi square root of I by mp. When the mass is quadrupled, it means it is made 4 times. Okay. So this m you should not confuse it with mass, because this m is the magnetic moment. Okay. So when the mass is quadrupled, you have moment of inertia here. Okay, moment of inertia here. So let us consider that initially the moment of inertia is I1. Okay, initially the moment of inertia is I1 equal to I, and that will be equal to mr square. Now the mass is quadrupled. That means I2 is equal to 4 times the mass into r square. Okay, I2 equal to 4 mr square. So from both these expressions, we can understand that the moment of inertia, okay, the moment of inertia is actually directly proportional to m. Moment of inertia is directly proportional to m from both these expressions, because I1 equal to mr square. After the mass is quadrupled, I2 equal to 4mr square. So r squared and r squared both are constants. That means moment of inertia is directly proportional to the mass. So here you have moment of inertia within the square root. Okay. So initially you have time period t, and in the second case the moment of inertia should be directly proportional to 4m. Here the time period is proportional to root I. Okay, time period is proportional to root I. So in the first case, the time period is proportional to root I means I is proportional to m. So it is root m. I think you can understand my point. Okay, here you see the time period is proportional to root I. Okay, so t is proportional to root I, and we know very well I is proportional to m. So from that we can tell that t is proportional to root m. Okay. So in the first case, t1 you have and proportional to root m. In the second case, the mass is made 4 times. So t2 is proportional to root of 4m, and when you take square root of 4, it will be t2 proportional to, okay, t2 proportional to 2 into root m. That means the time period is now twice T1. Okay, the time period is now twice that of T1. I think you can understand these explanations. So that is twice. So the time period becomes twice. Okay, I think you can understand my explanation. Even if you have any doubt, you can simply unmute yourself and you can ask your doubt. Okay, you should not hesitate, because it is a learning process for you. Okay, so these classes will be extremely helpful for you in your preparation for the upcoming NEET exam. So whenever you have doubt at any point, you can simply unmute yourself and you can ask your doubt. Okay, then only you can learn. Okay, learning is very important. Okay, question number 25. An iron rod of susceptibility 599 is subjected to a magnetizing field of 1200 ampere per meter. The permeability of the material of the rod is, okay. So they have given susceptibility value and magnetizing field value. They are asking us to find out the permeability of the material of the rod. Okay. So susceptibility given, magnetizing field given, permeability we need to find out. So in these kind of problems, you need to know the formula. Okay, formula connecting the different parameters given in question. So let us see. This is the formula mu m. Okay, mu m is nothing but the relative permeability equal to mu 0 into 1 plus chi. So chi is nothing but the susceptibility. Okay. So chi has been given in question 599 and B is 1200. Okay. So mu m equal to mu naught into 1 plus chi. So mu naught value It's 4 pi into 10 power minus 7 into 1 plus chi. Chi value is 599. So 1 plus 599 will be making it 600. So when you simplify this, you will be getting 2.45 into 10 power minus 4 Tesla meter per ampere. This is option D. Okay, simple solution. You have to just substitute the various parameters in equation and you can find out the solution. Okay. So question number 26. Here you see a thin diamagnetic rod is placed vertically between the poles of an electromagnet. When the current in the electromagnet is switched on, then the diamagnetic rod is pushed up out of the horizontal magnetic field. Hence, the rod gains gravitational potential energy. The work required to do this comes from, okay, they have given 4 options: the lattice structure of the material of the rod, the magnetic field, the current source, the induced electric field due to the changing magnetic field. So before that, you need to first understand the question. A thin diamagnetic rod is placed vertically between the poles of an electromagnet. Okay. So when the current is switched, when the current in the electromagnet is switched on, then the diamagnetic rod is pushed up out of the horizontal magnetic field. Okay. Hence, the rod gains potential energy. So let me draw the simplest diagram here. So here you are having the electromagnet, right? So this is the north pole of the magnet. And this is the south pole of the magnet. Okay, electromagnet. Electromagnet means it will gain magnetism only when you switch on the current. And you have a diamagnetic rod. Okay, diamagnetic rod. So I am drawing the diamagnetic rod like this. You have this diamagnetic rod. Okay, and this is north pole and this is south pole. So this is north pole, for example. Okay, this is north pole and this is south pole. You have this diamagnetic rod. So when you switch on this electromagnet, magnetic field lines start flowing. Okay, magnetic field lines start flowing. That means this electromagnet acquires magnetism after the current is switched on. So when the magnetic lines start flowing, the diamagnetic rod goes up. Okay, the diamagnetic rod goes up. In this process, it gains potential energy. Okay. So since it gains potential energy, work must be done. Okay, work must have been done. Okay, that work should be converted into potential energy. So work must have been done to impart potential energy to the diamagnetic material. What they are asking is, you should find out from where does this work come from. Okay. So for that, you need to understand that a diamagnetic material is having the weakest magnetic property. Okay. Diamagnetic material is having the weakest magnetic property. So when placed in a magnetic field, it always tries to move from weaker part of the field to the stronger part of the field. That means it repels the magnetic field. Okay. So usually the diamagnetic materials, okay, they actually repel the external magnetic field. So here the rod is repelled by the field produced due to the current source. Since the current source produces the magnetic field, so the diamagnetic rod actually repels the field produced. Okay, field produced by the electromagnet, and that field has come from the current source. Okay, so the repulsion has come due to the presence of the external magnetic field, and that external magnetic field is due to the current source. So the current source actually gives the work done. Okay, provides the work done. So current source, that is option C. And question number 27. Nickel shows ferromagnetic property at room temperature. If the temperature is increased beyond Curie temperature, then it will show. So it is a memory-based question. Nickel shows ferromagnetic property at room temperature. If the temperature is increased beyond Curie temperature, then it will show. Okay. So it is a memory-based question. That means nickel is a ferromagnet. Okay, nickel is a ferromagnet and it shows ferromagnetic property at room temperature. So Curie temperature is the temperature which is the critical value, which is the limiting value of temperature, above which the ferromagnetic material becomes a paramagnetic material. Okay, this is the limiting value of temperature. Okay. So when you increase the temperature beyond Curie temperature, usually a ferromagnet behaves like a paramagnet. Okay, this is the just a concept-oriented question and a memory-based question. So you need not confuse so much. Okay, into this. So nickel shows ferromagnetic property at room temperature, and the temperature is increased beyond the Curie temperature. It will show paramagnetism. So that is option A. Okay. Then question number 28. If the magnetic dipole moment of an atom of diamagnetic material, paramagnetic material and ferromagnetic material are denoted by mu d, mu p and mu f respectively, then, okay. So the magnetic dipole moment of diamagnetic, paramagnetic and ferromagnetic materials, they are represented by mu d, mu p and mu f. Then which of the following options is correct? Okay, here it should be option C. And why option C? Okay, so you see, usually the diamagnetic material, they don't have any permanent dipole moment. Okay, the magnetic property in a diamagnetic material is mainly due to the orbital motion of electrons. Okay, so the diamagnetic materials usually don't have any dipole moment originally. Okay, and diamagnetic material acquires magnetism. Diamagnetic material usually acquires magnetism in the presence of an external magnetic field only. Okay, so diamagnetic material doesn't have any dipole moment on its own, so mu d equal to 0. And in a paramagnetic material, it has its own dipole moment because it will be having unpaired electrons. Okay, the unpaired electron contributes to the magnetic moment, so it is non-zero. So mu d equal to 0 and mu p is not equal to 0. Okay, these are the equations. Option C. Then question number 29. According to Curie's law, the magnetic susceptibility of a paramagnetic substance at an absolute temperature is proportional to. Okay, according to Curie's law, and it is also a concept-based question. Chi is inversely proportional to T usually. Okay, the magnetic susceptibility. So you see chi, okay, is inversely proportional to T, the susceptibility. This is the relation. Based on that, option C is the right answer. Okay, right. Question number 30. Okay, so for question number 30, I would like to mention one point. In the answer key given by me earlier, I have mentioned that it is having a different answer, but actually the right answer is option D. Okay, in my earlier answer key, I have mentioned a different option, so that option is actually the different one. Okay, but the right answer is option D. So please make note of this change. Okay, so earlier I have in the answer key which I have given, okay, I have mentioned a different answer, but the correct answer is option D. And I will explain you how it is option B. Okay, for question number 30. So a vibration magnetometer placed in a magnetic meridian has a small bar magnet. The magnet executes oscillations with a time period of 2 seconds in the Earth's horizontal magnetic field of 24 microtesla. When a horizontal field of 18 microtesla is produced opposite to the Earth's field by placing a current carrying wire, the new time period of the magnet will be, okay. The magnet is oscillating actually. A vibration magnetometer is placed in a magnetic meridian as a small bar magnet. The magnet executes oscillation with a time period of 2 seconds in the Earth's horizontal magnetic field of 24 microtesla. When you have one more horizontal field of 18 microtesla produced opposite to the Earth's field, okay, now the new time period of magnet will be, okay. This is a question, and we have the formula to T equal to 2 pi root of I by M into BH. So I think this formula we have discussed earlier, T equal to 2 pi root of I by M into BH. So here the time period is inversely proportional to square root of BH, okay, inversely proportional to the square root of BH. In the question they have given us two scenarios, T1 and T2, okay, T1 and T2. So T1 by T2 means that is equal to root of BH2 by BH1, okay. So T1 by T2 equal to root of BH2 by BH1. So since it is the inverse proportionality relation, P is inversely proportional to square root of BH. So T1 by T2 equal to root of BH2 by BH1. So in the second case, what is the value of magnetic field? It is 24 minus 18. Why it is 24 minus 18? Earlier you have the 24 microtesla field, but in the second case they are giving an 18 microtesla field opposite to the Earth's magnetic field, okay. That means this Earth's magnetic field 24 microtesla is opposed by one more magnetic field of 18 microtesla. So the net field will be 24 minus 18. So here you have 24 minus 18, okay. So T1 by T2 equal to root of 24 minus 18 microtesla divided by root 24 Tesla, okay. So here T1 you know the value. So T2 you need to find out. So you can make the rearrangements of this equation. So in this process you will be getting T2 equal to 4 seconds. Okay. Simple mathematics, T1 by T2 equal to this equation, root BH2 by root BH1. Okay. So from that you can actually calculate. So 2 by T2 equal to root of 24 minus 18 by root 24. So you can cancel out everything. Then you can find out the value of T2. That is 4 seconds. Option D. Option D is the right answer. Okay. So these are the solutions for the questions. Okay. I hope you all might have understood the solutions. Okay. Students, do you all understand how to solve these problems?
Yes, sir.
Okay. Now we are moving on to our next lesson, that is electromagnetic induction. We are moving on to electromagnetic induction. So now I have opened the whiteboard. So in the electromagnetic induction, we have few important concepts which you need to understand first. Okay. So for that, let me draw a diagram initially. So you should consider that there is a magnetic field like this, a uniform magnetic field, so that the field lines are parallel to each other. Okay. The field lines are parallel to each other, represented by capital letter B. Okay. And these field lines are passing through this area. Okay, this is one area, and this area is inclined at an angle theta. Okay, this area is inclined at an angle theta, and the area vector is given by, before that let me differentiate this area by a different color, okay, so that we can understand it better. So this is the area. This area is inclined at an angle theta. The area vector is represented by vector A. Okay. So this magnetic field is passing through this area which is inclined at an angle theta. Okay. So this is the magnetic field. And now how to calculate the magnetic flux passing through this area? Okay. How to calculate the magnetic flux passing through this area? Magnetic flux is represented by phi, that is B dot A. Okay, dot product of this magnetic field, capital B. Usually it is called magnetic field, but the exact term for this B is magnetic induction. So phi equal to B dot A, vector B dot vector A. Okay, so since this is dot product, you can replace this dot by cos theta. So phi equal to BA cos theta. It is the expression for magnetic flux passing through this area, and magnetic flux is a scalar quantity. So what is the SI unit? SI unit of flux, do you know, students? SI unit of magnetic flux, what it is?
Sir, Tesla.
SI unit of magnetic flux is actually Weber. Okay, magnetic flux. I am asking about this phi. SI unit of magnetic flux is, it is actually Weber. Okay, it is actually Weber and represented by WB. Okay, WB, Weber. And Weber is nothing but Tesla into meter square, because phi equal to B into A. For magnetic induction, the unit is Tesla. For area, it is meter square. So this Weber is equivalent to Tesla meter square. Okay, so this is the SI unit, and there is a CGS unit for magnetic flux as well. CGS unit. So this is the SI unit. So what is the CGS unit? So that is also important. So CGS unit is also there for flux. What is the CGS unit of magnetic flux? That is Maxwell. Okay. CGS unit is Maxwell. So one Maxwell is nothing but it is 1 Gauss centimeter square. 1 Gauss centimeter square. And 1 Weber is nothing but 1 Weber is equal to 10 power 8 Maxwell. 10 power 8 Maxwell. Okay. Maxwell is represented by mx, the short form. So this is the CGS unit. And of course, you have the dimension of magnetic flux, which is also important, the dimensional formula. Okay. So the dimensional formula is important for a physical quantity, and you all might have learned about the dimensional formula in your 11th grade. Okay. So the dimensional formula for this magnetic flux, it is given by, so dimensional formula for magnetic flux phi is, it is m L squared T power minus 2 A power minus 1. Okay, T power minus 2 A power minus 1. This is the dimensional formula for magnetic flux. Okay. So this is how you need to understand the concept of magnetic flux, and So the concept of magnetic flux is very much important when we will be discussing the concept of electromagnetic induction. Okay, and we shall continue our discussion on electromagnetic induction in our next class. Okay, so please do the regular revision and keep on learning. If you have any doubt regarding any of the concepts, you are free to ask. Okay, so let us stop with this much, and we shall continue our discussion on electromagnetic induction in our next class. Thank you so much for joining the class.
Thank you, sir.
Thank you so much.